Okay, there's some handouts on one of the seats in the back, and I guess we should get going. Just to remind you a little bit of what we discussed the other day, we took a look at the types of propagating modes again, and I did mention the generalized piezoelectric, and here I'll remind you that in here all the field variables are coupled together. The other kind was the sagittal piezoelectric, in which the sagittal displacement or velocity fields and the electric potential are coupled. And then we have the shear horizontal type of mode, in which we have the transverse displacement or velocity field coupled to the potential. There are, of course, non-piezoelectrically coupled solutions which may exist, and if you recall, we looked at the reference, which is the article in the Physical Acoustics volume discussing the effect of crystal symmetry on decomposing or uncoupling different types of solutions, and there's quite a good list in there. The class of solutions we looked at really up till now has been the non-leaky lossless waves. Today I'm going to spend some time on the pseudo or leaky waves, and we'll introduce the idea of the high velocity pseudo surface wave. The one thing which is different, and I'll discuss that in more detail in just a moment, is that with the pseudo surface wave, I've got to narrow this down a bit, here we go. With the pseudo surface wave, the derivative with respect to the x or x1 direction is not just a phase constant, but there is an attenuating component in the direction of propagation. And that has an impact on what we have to do about finding solutions to such modes. The layered structure, I would like to refresh your mind that we ended up, in effect, having a cascaded multiplication of matrices corresponding to each of the layers until we got to the free surface, and then we had the sort of half of the eigen vector matrix corresponding to decaying modes in the substrate. That is the P sub P component, and the determinant of all of this is what I would call a dispersion relation, finding the values of the velocity which allow you to satisfy this, in fact give you the solution velocity to the problem. So that's sort of the background, and I did mention layered structures, and so while on that topic, let's take a look at what happens with layers. As I have mentioned before, when we are dealing with layers, we are in the situation where, in fact, that's fairly visible. We have more than one mode, and here I've just taken the example of the zinc oxide on diamond, which is something that some of you people are concerned with. And here, the first mode starts at the Rayleigh velocity for the diamond, which is 10.97, and it goes down and then goes all the way down to about 3 kilometers per second. The second mode starts at a cutoff frequency and falls down fairly rapidly, as shown over here, and goes down to a little bit less than 6 kilometers per second. I want to point out here that as far as I can determine, these first and second modes do not cross. There is a gap between those two curves, and that's sort of a numerically determined thing. The third mode starts off at a somewhat higher cutoff frequency and goes down. So all these modes go down in velocity as the frequency increases or as the thickness increases, and that's why, as the independent variable in my plot, I have the product of thickness and frequency. I find it a little awkward to use thickness times the wave number unless it's normalized to, say, a shear velocity or something, because otherwise every point is velocity dependent on both vertical and horizontal axes, and that's not a very good way of representing the function in my opinion. That's a personal opinion, of course. I'll come back to this curve again in just a moment, but I'd like to move on now to the issue of how we do in fact handle the pseudo surface waves. The key thing is to introduce some attenuation in the direction of propagation, and that's flagged by a small imaginary component in the bracketed term right after the omega over v quantity, and that's equivalent to the other relationship that I had on the first slide, which is, I think, also the first sheet I've recirculated again. And so, in effect, the derivative with respect to x has to be modified in formulating the equations from the word go, and so, as a result, the impact of this condition is that the material matrix, in effect, becomes complex. The eigenmodes that we have to use in order to arrive at a solution for the leaky or pseudo-so modes must include one growing eigenmode, and the boundary condition is now a function of two variables, because in the x dependence we have a variable which is the phase velocity and another parameter which is the attenuation constant alpha. It's convenient to write it as alpha times the wavelength, and that's usually the way people calculate the attenuation for pseudo or leaky surface acoustic waves. So we have two variables, v sub p and alpha times lambda. Now our boundary condition, to satisfy our boundary condition, we have to find the right phase velocity and the right alpha to make that function zero. And so we are in the situation with leaky or pseudo-so modes where we have to find the zero of a complex function of two real variables, and so the strategy for finding the solution is slightly modified, but it depends on what kind of software you're using. There's nothing inherently different about it. What I want to recapitulate, though, is that in order to find such a solution, of the four decaying modes with depth, you have to discard one of them and bring in one which grows with depth. You cannot have power conservation and have anything but a growth with depth and a decay along the x1 direction, because there is nothing in the formulation of this problem which allows for dissipation. We do not have any power loss mechanisms in here. So we have to have a conservation of power implicit in what we're doing. So if the wave is attenuating in its direction of propagation, it must be growing slightly in the depth. So we have to select, in order to satisfy the boundary condition, we have to select three of the modes which decay with depth, but one mode which grows slightly with depth. Now that one mode which grows slightly with depth, some people have called a quasi-bulk wave. No, it's a bulk-like component, because it turns out that it has got a dependence which is imaginary with respect to depth, and so it looks a little bit like a tilted bulk wave. If you look at the details of the solutions and take a close look at this additional mode that you've included and discarded one which decays with depth, you find out that it corresponds almost precisely to the correct tilted bulk wave which satisfies the propagation at a certain direction. Now this is going beyond the issues I want to raise today, but those of you who may want to look at that more deeply will probably want to look at this particular aspect. So to summarize then, what we do, if we're looking at pseudo-surface waves, we include an attenuation coefficient in the direction of propagation, and we take 4 modes to satisfy our boundary conditions, one of which grows with depths, and all the others are like the standard surface wave problem. And when you do that, then you find that you can satisfy the boundary condition to any level that you wish. And let me go back to the curve that we just had a moment ago, and which we can remove over here. And you'll find that the pseudo surface wave solution actually takes off right at the cutoff edge of the second surface wave mode, so that we can go on finding solutions to the surface wave problem all the way up to about 18 kilometers per second of velocity. And however, going along with this portion of the curve, there is a corresponding attenuation per wavelength. For this particular combination, it turns out that there is some kind of a minimum in the attenuation of the pseudo-SO mode at about a value of HF of 0.6. In fact, at HF of 0.6, the attenuation is about 2 dB per 100 wavelengths. So, although these are rather quickly calculated numbers, I haven't double-checked them. They're typical of the sort of things we get. And so, for the zinc oxide on diamond, the second Rayleigh mode goes into a pseudo-SO regime, which is what I call a high-velocity one. There isn't a slow-velocity pseudo mode for this combination, because it turns out that this is a purely sagittal piezoelectrically coupled solution. So there's only one pseudo-SO mode, and that pseudo-SO mode is the so-called high-velocity pseudo-SO mode. And it approaches the longitudinal velocity of the diamond as we approach zero thickness. So this is the sort of framework in which I've, on this particular curve that we've just looked at, which you all have, I'm showing you 3 modes for a layered structure, and I'm also showing on this particular curve the leaky part of what I'll call the second mode. One can probably extend the third mode and also find another branch which is pseudo surface wave type. So this is the background, and of course, as always, I welcome any questions that you have at this stage, because I'm going to just go through a few examples now. Yes, Lee?
Okay, this third mode that's coming out there, can you say offhand what that last mode of zero thickness, will that go to the same number?
Sorry, to which number?
Will that also go to the 18,000? The third mode, which you show presently cut off, you said that'll go into a pseudo surface wave. That also goes to a high velocity one?
Let me repeat your questions to make sure everybody's understood it here. The question is, will the third mode also asymptotically approach this longitudinal velocity? Without doing the calculations, I don't know. I suspect the answer to that is yes. So that at zero thickness, we really only have one point at which we can find a solution. I didn't bring the attenuation numbers except for that minimum that I just mentioned.
Now, in the sagittal plane, you still have the shear vertical bulk wave. Did any of them?
There's no bulk wave.
No, I mean, there is a bulk wave which is polarized in the shear vertical plane of velocity. Do any of them asymptote to that shear wave velocity?
Let me again repeat the question, Lee. What you're saying is there is a vertically shear polarized bulk wave for the diamond. That particular velocity is degenerate, so both the vertically and the shear horizontally polarized ones both have the same shear velocity for diamond. Okay.
About 13,000.
Yes, about 12.8. Yeah, that's right. So I don't know, unless it turns out when you look at the numbers in this neighborhood that you cannot cross into a leaky regime. I know that that has happened in some things I've tried in the past, but I haven't tried it on the diamond, zinc oxide on diamond. Something to be looked at. Any other questions? Okay, so what I want to do is take a look at a couple of examples, really more than a couple. So let's take a look at this next sheet. I do have some data, which I'm going to take a look at in a moment, for quartz, lithium niobate, lithium tantalate, and lithium tetraborate. I'm not going to do any boundary condition function plots. These are in one of the papers that is part of the reading material. And for the pseudo, just including the propagation loss, we have a two-variable minimization process to find the velocity and the loss, and we have to include tilted growing bulk modes. They're really tilted bulk-like modes. They're really not bulk modes. Everything is tied up at the boundary condition, and it is the boundary which holds these two together. They look very much like bulk waves, but they're really not bulk waves, and I want to stress that. And then, of course, I just showed you a moment ago the high-velocity pseudo-SAW for the zinc oxide on diamond combination. Now, I'm not going to go through all of the sheets that are in the handout, but I think I want to go and take a look at some of the data in the tables. This is probably there we go. One thing I want to point out in this table is that you'll find the lithium niobate first and second entries repeated as the last two entries. They are repeated, but new material data has been used in the calculations. This is an attempt to take a look and see whether in fact the so-called losses on the pseudo-SAW modes were very dependent on the material constant choice. And I don't want to go through all of these in major detail, but if we take a look at the first two, for example, if you look at the dB per wavelength for the pseudo-SAW solutions, you'll find that it is almost negligible for the open circuited case, for the orientation 0 minus 49, 0. This is the so-called 41 degree cut. And conversely, for the 26 minus 26 degree, you'll find that it is the short-circuited surface that has a very deep minimum in the propagation loss. This is very typical of calculating the pseudo-SAW attenuation for materials as a function of orientation. And typically, if I can just draw a picture here, if we do a rotation, for example, in a plane, and plot the loss per wavelength, very typically we will find very sharp minima. Okay, and usually this is a log scale, so indeed the minimum is extremely sharp, because remember the alpha to start off with is in the exponent, and we're now plotting that in a logarithmic scale again, so that it really is a very compressed scale. What happens, or what you typically find, is if this is the open circuited curve, then the short circuited curve will also have a minimum, but at a slightly different angle. And when you take a look at the movement of this minimum, you find that if you perturb the material constants a little bit, you get a very, very large positional change in this minimum. So attempting to hit the attenuation minimum in doing surface wave devices operating at these pseudo-SAW modes can be a very tricky point, and I don't know how our colleagues in industry are handling this. So maybe we can have a chat about that at some future point. This is reflected. Let's take a look at this. The very first one and the last but one. You see, if you take a look at your numbers, that the short-circuited loss is 0.043 dB per wavelength in the top one, and is 0.0144 dB per wavelength in the other one. So for a fixed angle, if you change the material constants slightly, you get very different attenuation losses. But very honestly, I think what you're really doing is jumping from a place here to a place there. So the sensitivity, I don't think anybody has done a detailed sensitivity calculation, but the sensitivity is mainly due to the fact that these curves come swooping down so sharply, so that small angular changes give you big changes in the attenuation, or small perturbations in the material constants move you up and down in a very steep portion of the curve. So these are things that the designers, of course, have to be concerned with. What is important in terms of the pseudo-SAW should be noted by comparing the velocities in the first column after the angle designation, where we have numbers in the 3,000 odd, with the next column over where the numbers are in the 4,000. So there's about a 40% higher velocity for the pseudo-SAW typically. If we choose, for example, this last row, we have about 3,700 meters per second for the true surface wave, and we have about 4,700 for the pseudo-SAW. Another thing which is of interest is the fact that some of these have got very high electromechanical coupling constants. If you look at the last two, they're in over 10 or higher percent. So that's created a lot of excitement in the SAW filter community, and a lot of devices currently made are using some of these pseudo-SAW modes. I have a few others to share for those of you who are interested in the. Some of these are repeated, by the way, but we have the same kind of a notation here. There's a few different materials that you'll find in that other sheet. By the way, some of the stuff that I have distributed, some of it has been published, and some of it will appear shortly. Quartz ATX propagating, quartz STX, we're dealing with 5 kilometers per second velocities, and here are the lithium niobate that we had before. In addition, there is the gallium arsenide. Now, this particular sheet also shows the polarization of the wave in the penultimate column. This is something we've talked about, but haven't really looked at, so I'd like to just take a quick look at this particular column over here. You'll see, if you take a look at the numbers, you'll see that virtually all of these pseudo-sol modes, the first three, it is the U2 component which is the largest. So it's almost quasi-shear horizontal. As you go to gallium arsenide, for example, it's not as distinct. However, as you go to the lithium niobate, it's really quite significantly larger. The U2 component is dominant. The computations normalize to the U1 component, which is why you see those numbers. So unless we are at an angle or a location where there is something very special happening to the wave, our experience has been that the pseudo-sol mode is usually got a very large U2 component, a V2 component. So that's for what I'll call the regular pseudo-sol solution. The next sheet, which also has not yet been published, so it is fresh stuff, is the high velocity pseudo-sol solutions, again for different materials. Some of these materials where we had a pseudo-sol solution appear again. So on some orientations and some materials, we have three solutions to the surface wave problem. We have the lossless standard surface wave solution. We have a pseudo-sol solution with some loss. We now have a high velocity pseudo-sol solution also with some loss. If you take a look at these, for example, the velocities are in the 5 to 7 kilometers per second. It's still quite a bit lower, by the way, than the zinc oxide on diamond we were looking at a moment ago. For a lot of these orientations, the deeper wavelength loss is quite small, and so I believe that some of these orientations should be looked at by the device designers to take a look and see what is really going on and whether in fact these numbers that we predict theoretically are in fact anywhere near what one would find experimentally. We have very little experimental data available on the attenuation of either pseudo-sol modes or high velocity pseudo-sol modes, which have only been talked about in the last year or so anyway. And if we take a look at the polarizations, you will see that in all cases it is the U1 component which is by far the largest, and the solutions in all cases are closer to the longitudinal velocity than to any other characteristic velocity of the problem. The last two, by the way, are orientations in which there is only a sagittal solution allowed. So you'll see there's some zeros in the middle of that penultimate column. So again, this is the kind of thing that we have been able to identify relatively recently. There is confirmation of the existence of these high velocity modes from Brillouin scattering experiments, and very recently also from surface acoustic wave device experiments. So if any questions, I'll be glad to talk some more about that. What I'd like to look at before leaving these is to have a look at show you what I meant by attenuation minimum by taking a look at a specific example. This is ST quartz, and the angle is it's a ST cut situation, And this is the high velocity pseudo-SAW solution. And you can see what I was talking about when I said there's a very large minimum in the dB per wavelength attenuation in the neighborhood of some critical angle. In fact, we go down from something like 10 to the minus 5 over here to something like 10 to the minus 14 at this minimum. And what's interesting here is that it's relatively flat, although this is a log scale, except near this critical angle. And what is quite remarkable is that this angle is precisely the angle which corresponds to the single-phase unidirectional transducer orientation. So we have a coincidence here. We're not sure whether the two are linked or not, but that is what we find in our calculations. The upper curve, of course, is the velocity. The dashed part is the bulk wave velocity as you go around the 90 degrees, and the solid with the X's is the actual high velocity pseudo-SAW solution. So this is the velocity and this is the attenuation going together with this solution. Yeah?
Is that dropped by 1/3 more?
We are, let me make sure, let's take a look at this. There's a YZ lithium niobate. Okay, we have a shorter than, whoops. I better widen this, yeah. We have a 1.5 and a 0.07, so that would be 7 dB per 100 wavelength. I think that if one were to do a scan with respect to angle, we would indeed find that there is a sharp minimum. Virtually any selection we've made and done such a scan, we have been able to find that. So I think that this is sort of in the nature of this particular thing that we have called a pseudo-SAW. In case you missed the question was, will high coupling materials also exhibit such large dips in the dB per wavelength loss for these pseudo-SAWs? And the short answer is yes, I expect that if one looks as a function of angle, one will indeed find that there are such deep minima. Yes, Lee?
Are there things like mechanical displacement components that go to zero near those zones? Or no, some physical explanation that you can have as to why the attenuation goes to zero? At that point, the mechanical displacement is zero.
No, if we just take a look at any one of these numbers, let's take a look, for example, at the ST 25 degree quartz. You'll see that at that angle there is the attenuation is 1.8 10 to the minus 5 dB per wavelength, and yet the polarization is quite, there's nothing particularly startling about the polarization. It's dark. No, it's piezoelectric.
What's missing that in terms of the other? As far as where there are only one set of numbers in.
I'm sorry, where? Okay, you mean the open circuited?
Yeah.
Okay, we in this particular case, thank you for pointing this out. Let me back off and repeat your question, which was, is there any component or anything special that goes to zero when we have such a deep attenuation? We have not seen anything of that nature, and if you look at the quartz that I'm pointing to right now, you'll see that for the short-circuited case, the polarization doesn't exhibit anything peculiar. However, you will notice that with the open-circuited situation, I do not have any numbers there. The reason is that up to now we have not been able to find the solution at that point. And this is why right at the beginning I said there may be pseudo-saws and there may be high-velocity pseudo-saws. There are places where we have not been able to find solutions. There's another one indicated on this particular sheet for some weird cut of gallium arsenide, where there is no solution put in for the open-circuited case. Now, gallium arsenide is a very weak piezoelectric, and we know from experience that with weak piezoelectrics, it is very, very difficult and very important precisely how you satisfy the boundary condition. You may have to go to 15 or 16 significant digits in order to satisfy it properly, whereas with higher coupling piezoelectrics, you really don't have to do that. You can be pretty sloppy about to how many figures you are finding the velocity. So there are some things that are still to be looked at, very honestly. Let me remind you or give you the anecdote that up to the mid-60s, it was thought that surface acoustic waves were rather unusual and strange things and would only occur on certain materials and along certain directions. It's only after the Lim's work that he was able to demonstrate that there was no material and no direction along which it was not possible to find a surface wave solution. And the problem was with people's numerical computational techniques and machinery. So it may be that we have a higher level problem of the same kind here as to why we cannot find solutions to that situation. Any other questions on that particular point?
Does your search routine allow for coming in with a short plane from infinity and moving down through the surface?
Not in its present form, no, but it's not a major change to do that. It's going to introduce some complications because you now have a finite volume region in which your electromagnetic field equations have to be properly formulated. Makes things a little more tricky. Okay, so let me try to summarize some of the things that we have done since actually starting this series. What I've tried to focus on is reviewing the system matrix approach, which is the one that my students and I developed over the last couple of decades. We have spent some time on the infinite half space, which is a non-dispersive problem, and we talked about the solution there. We discussed the free surface boundary condition as requiring three stresses to vanish, and then depending on whether there was a short circuit or an open circuit, we looked separately at the electrical boundary conditions. Today I describe the additional thing we have to include in order to handle pseudo-surface acoustic waves. Okay, and we concluded here by looking at some examples to illustrate both the saw and the pseudo-saw on piezoelectrics, and in here we also looked at the high velocity pseudo-saw. So I think that this concludes the formal part of the three lectures, I would like to spend a few minutes before closing this off to talk a little bit about some problems that you might like to have a look at on your own. So, the first problem that you find on that sheet is the question, find the dispersion relation for the plate modes of an arbitrarily oriented non-piezoelectric plate of thickness h. See if you can put together the things we've discussed over the last 3+ hours and see if you can write down the kind of equation, or the kind of statement that corresponds to a boundary condition constraint and which will therefore give you the dispersion relation. Let me just briefly remind you that for the surface wave problem, we had the statement that this is equal to 0 was our dispersion relation. Okay, and P sub Pu was that part of the eigenvector matrix of the problem. It was the upper part, the upper block, and it was the half of it corresponding to the modes which had a positive real part in the eigenvalue and therefore corresponded to decay with depth. So I'm looking for maybe something of this form. I don't want you to sort of grind out any algebra or go to any big and tedious computations. I want you to be able to pull together the concepts of, in effect, for this problem. So let me go back to the diagram for a moment. This problem has two boundary conditions. So when you impose the two boundary conditions, you're going to come up with a constraint of some kind, and you'll be able to form it as some kind of an equation that has to be satisfied. That's all I want you to see, that you can do that. The second problem I have is somewhat more challenging because it's calculating the driving point impedance of a plate resonator. So you have to solve a problem that has two free boundary conditions. You have metal electrodes on the top and bottom. So mechanically the top and bottom are free. Electrically the top and bottom are shorted or have a constant potential V across them. And you should be able to write some kind of an expression for the driving point impedance of this kind of a problem. The reference matrix methods one that was published a few years ago, which you all have a copy of, if you sort of look in there and you follow the discussion, this should not give you lots of problems. But if you can go through it, then I think you will gain a certain amount of insight as to the method and what you apply. On this point, I want to make another comment, and that is, when you use the matrix method, you're not in any place saying there is a velocity such and such, we have a transmission line. When you formulate the driving point impedance for this kind of a problem, you're going to get the driving point impedance which will include all the terms due to all the possible modes that can propagate. The difference between the plate problem and the propagating plate mode and this one is there's nothing propagating parallel. Everything is in the z direction. So in this problem, d by dx is 0. Problem number 3 is almost like the other one, except now you have a different boundary condition on one of the faces, because you're going to think about bonding this transducer to an acoustic medium. And you'll see how, if you can work out a driving point impedance expression. Again, this problem has no propagation parallel to the surfaces, so d by dx is 0. But you have a different boundary condition to satisfy here, correspond with comparison to the top one. I'm sorry, I should be up here. Here you have one free face. Here you have a face where you have to have continuity of everything, all the mechanical variables. I've made it a little simpler by saying the substrate is non-piezoelectric. So that's just an infinite medium. The fourth problem that I propose is to find the dispersion relation for interfacial waves. Those are sometimes called Stoney waves. So now we're dealing with two semi-infinite media, one extending upwards to infinity, the other one extending downwards to infinity. This is a problem in which there is propagation parallel to the interface, and I'd like you to see if you can write out a dispersion equation which tells you what you would have to do in order to find the velocity of such a wave if it exists. So these are four problems that some of you may like to take a look at. There's something else on the reverse of that sheet which I'd like to just mention in passing. There's a list of relations here which are fairly important when you're doing some manipulations sometimes. Okay, they're very basic matrix relations. They are simple statements about the fact that a matrix has a triple product factorization form, which is shown as number 1 down here, that any matrix can be written as the triple product of the eigenvector matrix times the diagonal eigenvalue matrix times the inverse of the eigenvector matrix. There's another thing that's important, is that the eigenvector matrix of E to the power of a matrix is the same as the eigenvector matrix of the original matrix. And so these are some of the things that are that you may find that you need to use, and in the acoustics problem we're dealing with, the matrix A is a function of the loss phase velocity, remember, and therefore the eigenvector matrix and the eigenvalue matrix are also a function of the velocity. And if you need to calculate a transmission matrix, there is an omega, an A, and an H, so that depends on phase velocity and omega, and of course H. Or, as you've noticed in my plots or in my calculations, I use the omega H or FH product as an independent variable. So that's where things stand, which I sort of suggest you might want to take a look at. Almost all of these kinds of problems, with the exception of the interfacial wave problem, you'll find plenty of hints in this particular article, which looks at a whole class, different classes of problems, and all of these fall into that class. So I think we've come to the end of the series, and I've enjoyed doing this, and I hope you have too. Any questions today?